Okay, so we are talking about discrete time signals and some of the ideas. Just a quick recap a very quick recap. I mean, this is the notation that we've been using for a discrete time signal, this x of n, right? Where the square brackets indicate that I'm talking about discrete time signal, and the index n is that index which takes values only over the integer side. So that's how discrete time signals are different than a continuous time signal, because the independent variable in a continuous time signal takes values over the entire real number line on the real number line. So therefore, the signal is defined over the entire real set, as opposed to that a discrete time signal is only defined for integer values of the independent variable, right? I mean, many of the ideas in discrete time signals are similar to continuous time signals. For example, we've talked about energy, we talked about power, we've talked about energy signals and power signals in the last class, except that we just replace the integration with summation. And similarly, as far as signal transformations are concerned, I mean, this is very much similar to continuous time, and that's why I will not spend a lot of time, actually no time here in the class. I'll urge you to go through these notes. Time shifting is x of n minus n naught, where this is a delay when n naught is positive, where there's an advance when n naught is negative. And I give you some examples of the notes, and I'm going to upload these as well. I mean, this is already on the notebook. And then there's time reversal, flipping around the axis, right? So all of this is there, even in odd signals, and things are pretty simple, right? So what we're going to start today is our discussion on discrete time periodic signals. And the ideas, once again, are very similar, right? So we say, okay, a discrete time periodic signal, a discrete time signal is periodic if, and I'm going to use a sign here, so let me not do that. Let me just write the English here. If there exists some integer n, and that integer, so when I say n is an element of the set Z, so that means the n has to be from the integer set, such that x of n plus capital N must be equal to x of small n for all values of the integer set n, or all values of the independent variable, right? So this just like what we had in the continuous time case, right? Except that the period now has to be an integer, right? And if this condition is satisfied, that means the periodic signal or the discrete time signal periodically repeats itself after capital N samples, right? So we're not talking about seconds here, right? But rather capital N samples, right? And if this is satisfied, just like we had in the continuous time case, I can claim, okay, if capital N is a period, then this small m times capital N is also a period, right? Where small m is an integer, right? For all n and m element of the integer set, right? And essentially what that, I mean, if I can say this in words, is KG, if n is a period, any integer multiple of n would also be a period, right? Fairly simple, right? Very, very similar to the continuous time case, right? So let me talk about some examples, right? So if I tell you that x of n is equal to, let me pull it up, right? So x of n is a signal which is equal to half raised to power n for 0 is less than equal to n is less than equal to 2 and is 0 otherwise. Is this a periodic signal? What do you think? I mean, is this a periodic signal or no? Right? So why is it not a periodic signal? And people say in the chat box it's not. So why is it not a periodic signal? it doesn't repeat, right? So I mean, if I were to sketch this out, if I were to sketch the signal out, I mean, what do I get, right? So this signal, if this is the n axis or the independent variable axis, right? This signal is going to be equal to 1 at n equals 0, and then it's going to be equal to half at n equals 1, and then is equal to 1 by 4. This is 0, this is 1, and this is 2. This height is 1, this is half, and this is 1 by 4. And for all other values of the index n or the independent variable n, this signal is 0. And it's not repeating itself, right? Now, let me give you another signal, and let me call that as y1 of n. And let's say y1 of n is equal to, let me say y of 1 of n is equal to summation k going from minus infinity to plus infinity, x of n minus 4k. What do you think about the signal y1 of n? I mean, what's really going on with the summation that you see? If somebody can try to explain to me, I mean, when you look at this expression, right? When you look at this expression, what does this tell you? Right? What comes to mind? I mean, what would y1 of n be? I mean, what are the operations that you're doing here? कौन बताएगा? Right? Adding every fourth peak. What do you mean by adding every fourth peak? Daniel?
Sir, fourth वाली मतलब कि 1 और 5 और इस तरह 9 लेकर
Okay. Right. Anyone else who has an answer? No? All right, so let me, I mean, what does this summation mean? Summation means that I mean, this is like an integral, right? Except that this summation means that you're summing over, it's like a for loop, yeah? You're iterating over the variable k over the entire integer set, right? So therefore, this k starts moving from minus infinity all the way up to plus infinity over every integer that exists in this set, right? So this, I mean, if I were to write this as what's really going on, this would be x of n. Let's say I start from k equals minus 2. So this is plus 8 plus x of n plus 4 plus x of n plus x of n minus 4 plus x of n minus 8, and so on and so forth, all the way up to infinity, right? So what's really going on is that this term actually corresponds to what value of k? Can you try to take a guess, or not guess, analyze? What value k equals minus 2? Excellent, right? So this is k equals minus 2, right? This value corresponds to the case when k was actually equal to minus 1. This is k equals 0, and this is k equals 1, and this is k equals 2, and so on and so forth. There are other terms here. So k equals 3, 4, and 5 all the way up to infinity. Similarly, minus 2 se pehle bhi. So there's a minus 3, minus 4, all the way up to minus infinity in the backward direction, right? So this, when you see the summation here, right? I mean, that's what you should come to your mind here. What's going on? I mean, this is actually summing of different shifted versions of x, right? As k moves from minus infinity to plus infinity. It's like a for loop, if you will. I mean, for those of you who are comfortable with programming, right? Now, and the expression up above here, this expression here, is a nice compact mathematical way of just writing out this long equation that I would have had to write had I just been writing each and every one of the term inside the summation. Okay? So the summation notation makes our life easy. Now the next question here is, I mean, if you understand what this summation represents, what is y1 of n going to be? I mean, if you were to sketch it, what would it be? Right? What would y1 of be? Right? If I ask you to sketch y1 of n, I mean, how would you do that? Oops. Anyone? Right? It will become periodic, right? So the analysis, it will become periodic. Why would it become periodic? And the answer is correct, right? So I see that the bunch of x's that are summing up, right? The bunch of x's and shifted versions of x's that you end up summing at the end, right? So if I just sketch what this x of n is, right? This x of n is something like this, right? Where this is 0, this is 1, and this is 2, right? So this thing in the pink thing here is x of n, and is 0 at all other places, right? And this is 3, and this is minus 1, and so on and so forth. What about x of n minus 4? What would that be? What would x of n minus 4, right? So the x of n minus 4 would just be this pink thing shifted to the right by 4 indices. Therefore, that's going to start at, instead of starting at 0, it's going to start at 4, right? So this is what x of n minus 4 is going to be, right? Where this is 4, this is 5, this is 6, this is 7. And so this is x of n minus 4. What about x of n minus 8, right? X of n minus 8 is going to start at n equals 8, right? So here's what x of n minus 8 is, right? So this is x of n minus 8, and so on and so forth, right? And similarly, x of n minus 12 is going to start at 12, and so on, right? So this is 8, this is 9, this is 10, and this is 11. Similarly, let's just go the other side just once, right? And what would x of n plus 4 be? What would x of n plus 4 be? I mean, that would start at n equals minus 4, right? So this would be x of n plus 4. So this is here, then a smaller one, and then a slightly bigger one, and then here, right? So where this would be minus 4, and this is minus 3, and this is minus 2, and this, whatever this color is, this is x of n plus 4, right? And so on and so forth. So x of n minus 8, n plus 8 is going to be something here. And this is minus 8, minus 7, minus 6, minus 5, right? This is x of n plus 8. And clearly, this y1 of n is periodic, right? So we say clearly the visual depiction tells you that y1 of n is periodic, right? What is the period for that, by the way? Or what is the fundamental period for this? Yeah, so the fundamental period is 4, exactly. All right. Now, let me ask you the following question, right? So if by this visual inspection, or by just looking at the expression and understanding what's really going on, and you figure out the fundamental period is 4. If I then ask you, why don't you just look at y1 of n? I mean, so here's y1 of n, right? And this is given as k equals minus infinity to plus infinity, x of n minus 4k, right? So that's y1 of n. If I, from this visual inspection, if I have figured out, as many of you have pointed out in the chat box, that the fundamental period for this is capital N equals 4, then I must have the following, which is if I compute y1 of n plus capital N, which is in this case 4 here, right? And if I just plug in k equals minus infinity plus infinity, I replace n with n plus 4, and then there's a minus 4k here, right? is this equal to y1 of n? I mean, if I just analyze it mathematically and you just question these things, is your visual inspection really correct or not? I mean, does the mathematics satisfy or validate your intuition that you've developed from the visual inspection? And is it or is it not? Right. So here's the big question: is this really equal to y1 of n? Because if it is not, then that means it's not periodic, right? And if it is periodic, you with the period equal to 4, you need to show that this thing here, you will need to show that this thing here must be equal to k equals minus infinity plus infinity x of n minus 4k, because that's what y1 of n is, right? Can somebody prove for me, Kiri, this is indeed true? Ji Manur.
Sir, I might not be good at putting it into words, लेकिन I think कि because इसका period 4 है, तो
Yeah.
अगर इसमें shift 4 की है तो it wouldn't really matter because वो फिर भी उसी point पर ही आके fix होगी उसकी value. Like अगर 0 वाला point अगर 4 shift हो, तो it would just go back to where it was.
Excellent, right? So, Manu, keep unmuted, right? So, what you're saying is if I just look at this, summation here, I mean, what's actually going on here is कि when k equals 0, तो shift जो है 4 पे होता है. When k equals 1, तो shift जो है 0 पे हो जाता है. और k equals 2 है, तो the shift जो है -4 पे हो जाता है. Right? But लेकिन the shifting is once again over integer multiples of 4. Right? It's just that the index has changed slightly. Right? जो shift k equals 0 पे पहले हो रहा था, अब वो shift जो है k equals 1 पे हो जाता है. Does that make sense?
Yes, sir.
Right? So,
Yes.
but other than that, when you're cycling through all of the shifts are 0 and plus minus 4, plus minus 8, plus minus 12, and so on and so forth, right? But can you then therefore the question is कि mathematically इसको किस तरह करेंगे? Your intuition is perfectly correct, right? इसको mathematically इस तरह करेंगे, and Ibrahim has the answer here, excellent, which is Ibrahim, ये आप unmute करके बोल देते तो शायद right, materialistic फायदा हो जाता आपको, right? So and Ibrahim tells me that you go from k equals minus to infinity plus infinity, the summation, and he tells me that you should take 4, or actually let me use a minus sign here, and this is 4 times k minus 1. Right, so that's a simple manipulation, and then I just can make a change of variables, right? So if I just let m equals k minus 1, then I mean clearly, I mean if k minus 1 goes all the way up to from minus infinity to plus infinity over the integer set, then k minus 1 is also going to go over the integer set from minus infinity to plus infinity, right? So here's goes m equals minus infinity to plus infinity, and from here x equals n minus 4 times m, and which is indeed equal to y1 of n. And here's the proof. Right, and I love your sentiment, Manu, which is why didn't I think that? Right, right. So, right, Ibrahim, मैं आपको दे रहा हूँ यार. Don't worry. You see, this is a regular pen, right? So I just wrote down your name. Happy? Okay. Now let me, as I always do, let me up the game a little bit, and I say, KG, let's say, so the bottom line is okay. The bottom line is y1 of n is periodic with fundamental period n equals 4. Now let me give you another signal, which is y2 of n. And y2 of n is summation going from k equals minus infinity to plus infinity. And this is x of n minus 6 of k. And going by the same set of principles, I can show, okay, this is periodic with what's the period? Six, right? So the period is n. So this is, let's say this is n1 and this is n2 equals 6. Now here's the question for you. And that question is, okay, if y of n equals y1 of n plus y2 of n, is y of n periodic? And if it is periodic, I mean, determine the fundamental period. Otherwise, if it's not periodic, just make an argument against that notion. Right? So what do you think? I mean, is this sum of, I mean, I know that y1 of n is periodic with a period of 4, right? So this was n1 equals 4, and this was periodic with a period of 6, right? So what is the, Hamza Rashid says it's periodic. Good, right, Hamza? Like period kya hoga? I mean, we've done some things like these.
सर जिस तरह कंटिन्यूस टाइम सिग्नल्स में हमने किया था एलसीएम ले लिया था दोनों पीरियड्स का, उस तरह इसमें
Excellent.
कर लेंगे.
Right? So that's 12, right? So so the period, so people go about this and LCM of 4 and 6, right? Excellent, right? So and so I don't really need to. So and the answer is yes, right? Right. So the answer to this is yes, and the fundamental period is 12, right? Because 12 is an integer multiple of 4 as the smallest integer of 4 as well as 6. Okay. And so these were just some examples to talk about periodic signals, discrete time periodic signals. Any questions? So Charlie, let me ask you a question here. So, or let me put this in the box here, right? So given two periodic signals, x1 of n and x2 of n, will x of n is equal to x1 of n plus x2 of n always be periodic? Right, so this is a question I'm leaving for you, right? So this is many times I've asked this in an exam, right? And make an argument, right? So not necessarily. Why do you say not necessarily, Manur? Or किसने नहीं बोला? Manur ने बोली है. Marine?
Sir, because we have done examples in the past, like when we were doing continuous, just like when we added them,
Yeah.
they weren't periodic. So
And
yeah.
when did that happen? That actually happened when the ratio of those two fundamental periods turned out to be irrational, right? I mean,
Yes.
so as Hassan says, rational irrational argument as well, right? Is there anybody who disagrees with everyone here? जो अभी तक जिसने भी answer दिया. Anybody who disagrees? जी मस्तान और उमर.
Sir, I disagree because we said that all in discrete time signals the separation should be integer numbers, so integer
Yes.
numbers cannot be irrational.
Excellent, right? So this is actually true. The statement is actually true, right? So because the x1 has a period which is an integer, x2 is a period which is an integer, and you will always be able to find an integer which is an integer multiple of the first one and an integer multiple of the second one, right? So that's the real point here. Okay, so when you're thinking about these things, right? So I mean, it's important that you don't just bring over the arguments from before just because you memorize them, right? And that's what actually happened over here, right? Because there's something that you memorized, right? But not really figure out wo kyun true tha, right? So the why is extremely important, right? So make sure you know why a certain results hold and under what conditions does it hold, okay? All right. So what I'm going to do next is start our discussions, which is extremely important. And that discussion is regarding discrete time complex exponentials, right? So let me give you a recall of the continuous time periodics complex exponential, right? So we had x of t was equal to e raised by j omega naught t, right? Which was cosine omega naught t plus j sine omega naught t, right? So this is something we know, and this is just a sketch of the real part of x of t, which is actually a cosine, and the imaginary part of x, which is a sine. And this particular illustration is for the case when omega naught is pi by 2 radians per second, or which is t equals 4 seconds, right? This was a continuous time case. Now, another way to visualize this complex periodic continuous time exponential was to collapse the time dimension. Well, I mean, so if you looked at the animations that I put up and made myself, which was KG, a complex exponential is actually nothing but a spiral, right? And that spiral is actually in 3 dimensions, right? The first dimension is the real part. The second dimension, which is going inside the paper, is the imaginary part. And the third dimension, which is perhaps the x, is actually the time dimension. As time increases, what you have is a spiral, which is moving in a circle, right? So one of the things to just look at that and make the visualization easy is to go here and start looking only at the projection of that spiral on the real and imaginary axis, right? So in other words, here's what the complex exponential, which is a continuous time complex exponential, would look like. If this is the real part of x of t, and this is the imaginary part of x of t, right? So then what does a complex exponential look like in this domain if I've collapsed the time dimension, right? So I've not been able to look at the time. ठीक है, मैं time के इस तरह x में खड़ा हूँ, time मेरे अंदर मेरी तरफ आ रहा है, right? So therefore I cannot actually look at the time, right? So it looks like a circle. Excellent, right? So, and the circle, I see a point moving on the circle, right? So if at time t equals 0, this is where the point was, right? And so let me draw a circle here. I hope it's good enough. Right, imagine that this is actually a circle, okay? I think I can draw a better circle here, right? So if this is a circle here, what's actually going on is at time t equals 0, this is where your spiral is. And as time increases, if omega naught is positive, this spiral starts moving along this circle, right? And how fast is it moving? That depends on what your frequency is, right? And that frequency is omega naught radians per second. That means within 1 second, the circle is going to cover omega naught radians. For every second is going to traverse an angle of omega naught radians. Okay? So that's what a complex exponential really is, right? So, let me just demonstrate that, but this is omega naught, right? Now, let's talk about a discrete time exponential. So discrete time exponential is of the following form, right? So discrete time exponential or discrete time complex exponential. Ajit Alha.
So my question was, I understand the concept of this imaginary axis,
yeah.
But if we are, अगर इसमें time if we are considering that we're not using it time in this frame, so there is no time. So shouldn't I be able to see all of it at once? And engage of movement where a point carries, there will be one point. I will be able to see one point move. Since it is same to everything else, so
okay, so I
shouldn't really be able to.
Referring to असल में real time के साथ कुछ हो रहा है या फिर signal पहले से मौजूद है, right? So what I was referring to was some real time. If I just start, let's say the signal is already there, Okay, but I start looking at the signal, what it looks like by myself traversing the time axis. Let me see how the function behaves as I move along the time axis.
Okay, ठीक है. What I was thinking is कि अगर time, there is no concept of time there, so I should be able to see all of it at once.
Yeah, लेकिन जो है, let's say that there is a concept of time. क्या असल में real time signal आ रहा है.
Okay.
Right. As my speech in the real time is going to you, that's actually made up of this spiral. Believe it or not.
ठीक है. So, thank you.
Right. So this is discrete time complex exponential. All right. So discrete time complex exponential is just defined as x of n, which is equal to e raised to power j omega naught n. Very, very similar to a continuous time exponential. Except what's the difference here? I mean, what's the difference between this and x of t, which is e raised by j omega naught t?
N has to be an integer always here.
N has to be an integer. Excellent. N has to be an integer, right? So essentially what the signal that you're getting is no longer described or defined over the continuous time, but rather only over integers, right? So let's first of all try to see the case. Let's the omega naught equals pi by 4 वाली जो हमने निकाली भी हुई है, right? So if omega naught equals pi by 4, right? So then what does the discrete time signal look like, or the real part of it and the imaginary part of it, right? So I'm going to use the pink color to depict the discrete time exponential, and clearly this is equal to, this is cosine omega naught n plus j sine omega naught n, right? So this cosine omega naught n, because this omega naught is pi by 4, is exactly this signal here, which is a cosine, except that is defined only for integer values of time, which is n. ठीक है? तो फिर आपको कहाँ वैल्यू मिलेगी? एक वैल्यू मिलेगी आपको over here, right, at n equals 0. The other one is at n equals 1, which is going to be over here. The next one is going to be at n equals 2, which is over here. What went wrong? Yeah, so 0 here. Sorry, this is not 4. Sorry, this is 4 here. Right, and this is 3. This is 3, right? So this is the n equals 3, and this is at n equals 4, right? So it's like goes up, +1 and 0, -1, 0, and then +1, goes back to +1. And what about the sign here? Sign is going to be 0 here, 1 here, and then 0 here, and then -1 here, and 0 again. So the imaginary part. Now what happens on the circle? If I just collapse the time dimension, what I get is n equals 0 is the point is over here, right? Because n equals 0 pe kya hai? N equals 0 pe, this is the cosine omega naught n is actually 1, and the imaginary part is 0, right? Which is clear, right? Which is an angle of 0 degrees, right? What about n equals 1? What happens at n equals 1? Right, so what is x of 1? So let me use what color? What is x of 1? X of 1 is just simply e raised to power j pi by 2. And where is this point going to be? This point is at 90 degrees, which is here, n equals 2. Right? And what about n equals 1? What about n equals 2? So x of 2 is e raised to power j pi by 2 times 2, which is equal to e raised to power j pi. And that point is where? That's on the negative x-axis. And then this, so this is n equals 2. So this is n equals 3, right? And where does the n equals 4 occur? N equals 4 पे क्या होता है? क्यों Zen? What do you think? N equals 4, what happens at n equals 4? Same as n equals 0, right? So it's actually you're moving around in circle, except that what you're saying is that you're not completely looking at the circle, you're sampling it, right? So you wait a while, and by that time, the continuous time circle has actually traversed 90 degrees, and that's where you sample it, right? So that's n equals 1. And then you close your eyes again and wait for another time period, right? And 1 second. And by that 1 second, that has moved on to n equals 2, which is an angle of 180 degrees, and so on and so forth. And n equals 3 ke baad n equals 4 it goes back at n equals 0 and keeps on rotating once again, right? So once again, this is, I mean, the discrete time as well, this is a circle, right? And you will see, albeit some discrete points on the circle, but you'll see equally spaced points on the circle anyway, right? And there are 4 of them at this point, okay? So, and if you see the progression, you're going to see the progression like this, right? Ye idhar ja raha hai, right? N equals 1, n equals 2, n equals 3, and it takes 4 samples to complete the circle, okay? Now, let's try to extend the same sort of ideas to different sort of frequencies. Let's say omega naught. जी हमजा.
सर इसमें आपने ओमेगा नॉट पाई बाय 4 लिया, पाई बाय 2 लिया?
Thank you. That's actually pi by 2. Thank you, Hamza. I mean, somebody should have pointed this out before, right? So, and then let me try out pi equals 4. What do you think, Hamza? अब क्या होगा?
सर अब 1 और 0 1 जिस तरह हमने n equals 0 n equals to 1 के दरमियान एक और होगा पॉइंट.
Excellent, right? So, but it's still on a circle, right?
Yes.
Right. So this is the real part, and this is the imaginary part, and then there's a circle residing here, and the points now that you're going to get, n equals 0 पे ये point आ रहा है. As Hamza said, n equals 1. So let me, Hamza, note down your name. Right, so n equals, this is n equals 0. This is n equals 1. This is n equals 2. This is n equals 3. This is n equals 4. This is n equals 5. N equals 6. N equals 7. And n equals 8, it goes back, right? So circle completes at 8. Excellent, Manu. Okay? And then it's periodic, right? So remember, I mean, this is a periodic. At omega naught equals pi by 2, we periodic tha with a fundamental period of capital N equals 4, because that's where it starts repeating itself. Now it's a circle completes at 8. So this exponential is periodic with a period equal to 8, right? And once again, you will see this kind of a movement, right? This is the circle rotates. So you'll see, I mean, even if you're looking at discrete point, you'll see pehle idhar hai, phir idhar hai, phir idhar hai, phir idhar hai, and so on and so forth, right? Achha. Let me now discuss how things become interesting. Let's say this omega naught, I increase the frequency beyond pi by 2 and say, let's see 3 pi by 2, right? Which is 3 pi by 2 is 270 degrees, right? See if I can get rid of these. Oops. Right, so okay. So this particular case is omega naught equals pi by 4. This particular case is omega naught equals pi by 2. And let's try the case for so once again, I have a circle. Okay. What happens at n equals 0? Where's the circle at n equals 0? Should I draw a better circle? not so better, but nevertheless. N equals 0 पे कहाँ पे है? What do you think, Umar?
Zero पे ही होगा.
0 पे होगा. Right, excellent. Right, so n equals 0. The point is here. Now here's what about n equals 1? Roshin?
Yeah, minus here.
Right, so minus a. Roshin, what do you think? When omega naught equals 3 pi by 2, where do you think the point is going to be when n equals 1? So you want to traverse an angle of 3 pi by 2 radians, which is 270 degrees, or which is actually minus 90 degrees. Right? So at n equals 1, where would this point be? This is where the point is going to be. This is n equals 1. You see, it's actually going in a counterclockwise direction, but it has traveled the distance of or a radial distance of 270 degrees, right? Because of which it goes back down below, right? Now,
Sir,
Ji Roshan.
can you repeat this? I didn't get why n equals 1 is over there.
Right, so n equals 1, you see, x of 1 is e raised to power j 3 pi by 2, because that's the frequency times 1. Right? So 3 pi by 2, what angle is that? Ji Roshan, 3 pi by 2 कितना होता है?
Is it like 270?
Yes, it's 270 degrees, right? Which is minus 90.
Oh, okay.
That's the minus
Okay,
90 is
sir,
minus
got
8.
it. Okay, thank you, sir.
ठीक है? अच्छा, so this is where n equals 1. What about at n equals 2? Chale, who's going to help me here? Chale, Roshin, let's see if you can help me once again. What about n equals 2? Now, in going from angle n equals 1 to n equals 2, you need to traverse a distance which is equal to 270 degrees. Right? So यहाँ से move करना शुरू करना है. Right? यहाँ से move करना शुरू करना है. कितना move करना है?
You get 3 pi, so is it 180 degrees?
Yes. Right? So this is where you stop, right? And which is 270 degrees. And so this is going to be hard too. Right? So this is where you stop, and which is 180 degrees. And this is n equals 2. And what about n equals 3? You traverse another 270 degrees, and the answer is n equals 3 here. ठीक है? अच्छा. You see anything interesting?
Sir,
जी माज.
I didn't get the point where मतलब आपने शुरू में नीचे से clockwise किया बाद में anti clockwise क्यों किया 270 पे?
I'm always doing counterclockwise with 270 degrees, always. But you know what? Moving clockwise by 270 degrees is the same as moving anti-clockwise. Sorry, my bad. Right? I have always moved counterclockwise 270 degrees. Okay? Always. But moving counterclockwise by 270 degrees is exactly the same as moving clockwise by 90.
Clockwise in 90. वो तो समझ लगी, वो तो first n equal to 1 पे किया ना, you moved clockwise 90 degree. But second आपने n equal to 2 पे उसी को ही continue क्यों नहीं किया फिर?
उसी को किया. Right? n equals 1 से जाएंगे.
n equal to 1 पे है ना, अब यहाँ पे 90 पे आया था. तो वो आगे clockwise को ही आपने continue क्यों नहीं किया नीचे से 180 पे जाने के बजाय? अब you took reverse direction, मतलब आपने फिर वहाँ पे anti clockwise पूरा 270 घुमा के इधर किया.
Which is exactly the same as moving 90 degrees, right? So once again, as I said, KD, 270 degrees moving counterclockwise is exactly the same operation as moving 90 degrees in the clockwise direction. So either I move there or I move here, दोनों से end result तो एक ही आना, right?
हाँ ठीक है. अच्छा ठीक.
Right? So because x of 2 is x of 1 times e raised to power j 3 pi by 2. You can go ahead and verify this, right? इसका मतलब जहां भी x of 1 था पहले उसमें से 270 degrees add कर दें. That would be like subtracting 90 degrees.
ठीक है sir.
Because adding 270 is the same as subtracting 90, right? So n equals 2 here. अच्छा, I mean, so there's something very, very interesting I wanted to point out, which is even though your frequency is 3 pi by 2 radians per second in the continuous time domain, right? Which is high. What appears here? यहाँ पे दिख क्या रहा है आपको? If you're just looking at the samples, what goes on? You see n equals 0 पे उधर है, but the direction of motion that you see n equals 1 पे नीचे आ गया, फिर n equals 2 पे फिर ऊपर चला गया. So the perceived direction of motion as far as these dots, pink dots are concerned, appear to be in a clockwise direction, as opposed to the continuous time, which was moving in a counterclockwise direction. Right? Isn't that something which is extremely interesting? Right? I mean, that should amaze you at least. I mean that excites me, right? And there's a parallel that I can show you. Pankha agar chal raha ho badi tez, have you ever noticed or perceived the fan to be actually moving in the opposite direction to which it's actually moving? Right? Ever wonder why that happened? Right? कभी तने इतना कुछ ऑब्जर्व करते हैं जब तो सोचते भी तो होते हैं ना कि यार ये क्यों हो रहा है? Yes, I googled it. That's excellent, right? So at the very least, you should have googled it. So Tala, what did you find when you googled?
Camera में तो there was an explanation कि why this happens when we are looking it through a camera, क्योंकि उसके वो there is a thing about the shutter. I couldn't really find any explanation for why our eyes perceive it that way.
Okay, excellent, right?
So yeah, मुझे Google पे कुछ नहीं मिल जाता इस बार.
Let's go back to the rolling shutter, right? With the shutter example that you gave me, which was कि जी shutter में तो समझ आती है, उसी समझ आती है, because what the shutter is actually, or the camera is actually doing is, it cannot actually gather, or video camera cannot gather the continuous signal, right, or continuous beam, right? वो समय करता क्या है? It takes snapshots, in fact, right? It takes snapshots, and that's a discrete time signal, right? And by the way, so this is a tangent here. I can show you videos where, so we our group was trying to build a so there's a manufacturing industry mein, the paper goes up with a very, very high speed, right? And packaging ho rahi hoti hai, uske upar printing ho rahi hoti hai, and you can't really see what's going on because it's moving so fast, right? But you need to observe कि यार visually observe कि सही print हो रहा है नहीं हो रहा. You know what they do? They do exactly apply the same principle. They put that paper in a dark room and और फिर they shine light on it. That's called strobing, right? एक दफा shine करते हैं फिर छोड़ देते हैं और फिर अगली बार ऐसे शाइन करते हैं कि आपको लगता है कि पेपर उधर का उधर ही है, right? So even though it's actually moving so fast, right, you're just looking at snapshots, and that in that camera, and that's through the snapshot you stitch together as it looks as if it's completely still.
हम frequency match कर देते हैं उसकी.
But that's another tangent here. Let's go back to the eyes. And why does it appear to you? That's because your eyes also work like that shutter camera. Right? They cannot, your eyes or your nervous system cannot sample that continuous scenery. What actually does that? Tuck sampling. Right? And that's why you perceive things to be moving in the opposite direction, just like what we do here. असल में वो जो है 3 pi by 2 radians per second में move कर रहा है, right? But when you sample it at n equals 1 and 2 and 3, what appears to be that the circle moves to be moving in the other direction. ठीक है? Right. It's not just about the direction, Manwood. Let's talk about the next case. And this next case is omega naught equals 5 pi by 2 radians per second. Right? And this 5 pi by 2 radians per second, just to ease whatever I'm going to do next, is actually equal to 2 pi, because 5 by 2 is 2.5, right? So this is 2 pi plus pi by 2. Right? That's how many radians it is, right? So, right, so let me erase all this up and see. So this moves, appears to move in the other direction. And this corresponds to omega naught equals 3 pi by 2. Now let's see what happens with omega naught equals 5 pi by 2. And another circle, right? This is the real axis. This is the imaginary axis. Now, at n equals 0, of course, you're at 0. Or at n equals 1. Think of the angle is 0, right? What happened? So what did people say? I didn't get in the chat. कोई unmute करके बता दे मुझे.
सर वो बस किसी ने कहा था कि ओह सॉरी
that's fine.
So मैंने कहा था कि सेम पहले वाले ग्राफ की तरह हो जाएगा π/2 वाले की तरह.
Excellent, right? So what's actually going on here is, and I think Tala wanted to say the same, right? What's happening here is you're moving with, which is an angle equal to 5π/2. तो आप move कर रहे हैं इधर ही, करें 2π move कर लिया, 2π move कर लिया, और फिर move करने के बाद you find out कि यार अभी अगर मजीद और 5/2 जाना है, फिर ये 2π जाएगा, so that you end up being here. So you've actually completed an entire revolution, right, of 2π radians of 360 degrees. And then after 360 degrees, you have to move another 90 degrees in the counterclockwise direction. And that's what you do, right? So that you end up being here, n equals 1. And then from n equals 1, you need to traverse another, this 360 plus 90 degrees. So you traverse another 360 degrees, you're back where you started, and then another 90 degrees. So that's where you have n equals 2. And then here's n equals 3, right? So this is omega naught equals 5π/2. And this appears to be, actually is the same signal as omega naught equals π/2, right? So this is where discrete time complex exponentials differ from continuous time complex exponentials. Okay, continuous time exponentials there was a uniqueness with respect to the frequencies, right? No matter what frequency so for every frequency that I give you, I have two frequencies which are not the same. Those two continuous time periodic exponentials are going to be unique and different signals. This is not the same in discrete time. So if it is possible for you to get two frequencies in the discrete time, yet the signal turns out to be the same, right? And this is what we're going to try to formalize now, right? As we say π/2 and π/2 plus 2π is exactly the same frequency. So can somebody generalize this for me? What do you think the general result should be there, therefore? Right, so the bottom line is there is a periodicity in frequency. For the case of discrete time complex exponentials, right? What I mean by that is if I, yeah, excellent, Tala, right? So and Hassan, right? So this is if x of n is equal to e raised to power j omega naught n, and then let's say this is x1 of n, and I give you another signal which is x2 of n, which is e raised to power j omega naught, which has a frequency of e raised to power j omega naught plus 2π times n. So the frequency is omega naught plus 2π, right? If I just look at x2, I see that this is equal to e raised to power j omega naught n times e raised to power j 2π n. But what is e raised to power j 2π n? E raised to power j 2π n is 1. Excellent, right? And therefore, this is x1 of n. Right? So x2 of n turns out to be equal to x1 of n. Right? So therefore, the frequency, what we found out, that the frequency omega naught in discrete time is exactly the same as the frequency omega naught plus 2π in discrete time. Right? So there's a wraparound effect of frequencies, which is there in discrete time, which was not there in continuous time. Right? So that's the fundamental difference. That's a big difference. Right? So, the conclusion is that the frequency omega naught, any frequency omega naught, is the same as omega naught plus 2π, and actually plus any integer multiple of 2π, right? Which is, so the answer is omega naught I believe percent से मुराद आपकी जो है C++ वाले percentage है, right Daniel? Right, so this is modulo 2 pi. All right. Now, what does that therefore mean? कि जी इसका मतलब ये है कि discrete time में the unique frequencies only reside over, and pay attention to this, in discrete time, the unique frequencies are only going to reside in an interval of 2 pi, right? Beyond that interval, there's going to be a wraparound. अगर मैं आपको 0 to 2 pi की frequency set दे दूं, any frequencies outside of this interval 0 to 2 pi is going to map back to the frequency, the same frequency, right? So therefore, there's no need to consider frequencies greater than 2 pi for that matter. ठीक है, क्योंकि वो any frequency, for example, 3 pi है, that actually corresponds to pi, right? Or 5 pi actually corresponds to pi as well, right? So the important frequencies are only within an interval which is of 2 pi, only in discrete time. Okay? So, so this implies that the uniqueness is over an interval length of frequency. So typically what we do is we say, Kiji, either we take 0 is omega naught is less than 2 pi, right? So that's what we say. That we only consider, or you can say, chalo, isna kya lete hain. Okay, so typically we consider omega naught to belong to the set, a continuous set of frequencies between 0 and 2 pi, or alternately between minus pi and plus pi. Right? Both are equivalent. Okay? जी माज.
तो अगर हमारा ओमेगा 2 पाई होगा, so we'll consider it as 0 or 2 pi. 0.
बिल्कुल. 2 pi is 0. Excellent. जी उमर.
ये आपने ऊपर कॉम्प्लेक्स एक्सपोनेंशियल का जो सर्कल होता है उससे आपने बात की है, तो कंटीन्यूअस टाइम में भी तो वो रिपीट ही करती है 2 पाई के बाद तो सर्कल में वैल्यूज
they don't repeat. That's
मतलब सर्कल पे हमारे वेक्टर की पोजीशन तो वही आ जाती है ना.
So what I'm saying here is if I plug in a frequency of omega naught in the discrete time exponential and another frequency which is omega naught plus 2 pi in this exponential, the two signals that I get are going to be exactly the same signals for all values of n. That's what I'm saying, right? Could you say the same for continuous time?
No, sir, उसकी frequency ज़्यादा होती है.
Right, so उसकी ज़्यादा होती है ना. I cannot say if x1 of t is e raised by j omega naught t and x2 of t is equal to e raised by j omega naught plus 2 pi. I increase the frequency. So दोनों signals same है? They're not the same. And the reason is what? The reason is because t is not an integer. T can take on any values over the real number line. Yes, for integer values of t, both of them are going to be the same. But that's not enough to say that the signals are the same, because the integer value of t is just a tiny infinitesimally small set compared to the real number set. ठीक है, तो कुछ पॉइंट्स पे सिग्नल सेम होंगे, लेकिन सारे पॉइंट्स पे सिग्नल सेम नहीं होंगे.
एक्सक्यूज मी सर.
जी जैन.
सर पर हम लोग एक टाइम वो उसमें देखें फॉर, अगर हम लोग लाइक कंटिन्यूअस सिग्नल देखें जो पीरियोडिक हो, उसके तो हम शायद कह सकते हैं कि लाइक अगर t जो है वो पाई का मल्टीपल है, 2 पाई का मल्टीपल है, तो उसमें सेम ही होगा या उसमें भी नहीं है, जनरलाइज कर सकते हैं.
नहीं, I'm not saying anything about t here, right? So there's a difference here. Yes, there's periodicity in the continuous time with respect to time, but what I'm talking about is periodicity in the frequency.
Oh yeah, yes, ठीक है. अब
frequency omega naught और frequency omega naught plus 2 pi बराबर है.
जी सर.
So that's slightly different.
Yes.
Not slightly, but completely different. Okay. Acha. Right. So that's the first point. So the frequencies are not unique in the continuous time and the they're not unique in the discrete time. Right. So that's point number one. That's how discrete time exponentials are different than continuous time exponentials. Here's the second point. What can you say about the rate of oscillation? or how fast or how slow does the signal move or oscillate or change? Umar, do you have a question?
No, sir, वो पहले से
Okay. So here's this another interesting thing, right? See, if you go back to these examples that we saw, right? So at omega naught equals 0, I mean, you would expect the signal to stay constant. I mean, वो 0 पे रह रहा है, theta equals 0 पे रह रहा है हमेशा, right? So always stays equal to 1, right? And then pi by 4 and then pi by 2, right? Pi by 2 is a higher frequency. Pi by 4 is a smaller frequency. But what about 3 pi by 2, right? 3 pi by 2, which is 1.5 pi. 1.5 pi is actually greater than 0.5 pi, right? So where was pi by 2? Yeah. So this is pi by 2, right? So this is the case for pi by 2. यहाँ पे rate of oscillation क्या था? यहाँ पे rate of oscillation 4 samples था. So you completed an entire revolution in 4 samples, right? And this was 3 pi by 2, right? Which is greater than pi by 2. How many samples did you take here to complete the revolution? In this case, how many samples? This was still 4, right? Albeit in the other direction. So that means कि आप जब frequency बढ़ाना शुरू करते हैं, right? So that does not decrease your period always, right? So the thing that you mentioned, Muaz, is not true in discrete time. That means कि in continuous time, we know कि greater the value of omega, the faster the rate of oscillation. But that's not true in discrete time, right? And as we've been able to provide a counterexample, I've given you a counterexample where the frequency was pi by 2 and the frequency was 3 pi by 2. And in both cases, the rate of oscillation was exactly the same. Because in both cases, you completed the revolution in exactly 4 samples, albeit in other directions, right? So this runs counter to what you just mentioned in the chat box, okay? So then the question is, what is the highest frequency in discrete time? What do you think? So Talha ne kuch bola tha, pi by 2 ka kuch bola tha. What do you think would be the highest frequency in discrete time? Right. So I mean, if I can, I mean, if this is the omega naught frequency, right? Let me just look at this was 0 access pay, or this was 2 pi, right? This was pi by 2 and this was 3 pi by 2, right? And what we found just by simple observation is that the rate of oscillation at both of these frequencies is exactly the same. Right, so people try to answer this in the chat box. I've not had the correct answer yet. So what is the highest rate of oscillation? I mean, what frequency does the highest rate of oscillation correspond to, right? And I can try to give you an insight as follows here, right? So if I give you, let's omega naught, let that be within this interval, right? So now I have the right answer, right? So why do you think Talha pi is the answer?
Because either side of pi is actually जो मैं 1 वाली बात कर रहा था, 1 is equal to pi यहाँ पर होता है.
Yeah. So either side of pi. You're absolutely right, Talha. Absolutely right. Right. So pi is a band in the middle, right?
I could actually make sense of it in terms of 0.5 and 1. लेकिन मुझे pi के terms में थोड़ा समझ नहीं आ रही थी.
Right. So pi.
But yeah, the graph.
Okay, good. Right. So here's how. So if I give you omega naught, which is between 0 and pi, and I give you x1 of n, right? So so x1 of n, which is equal to e raised by j omega naught n, and then I give you which is x2 of n, which is e raised by j 2 pi minus omega naught times n. In other words, what I'm saying is, यार once again you look at this axis, ठीक है, यहाँ पे कोई भी omega naught ले लें, right? So let me use another color here. यहाँ पे कोई भी omega naught ले लें, ठीक है, which is this is omega naught, and उधर से 2 pi by omega naught ले लें, right? So your equidistance from 0 and 2 pi, right? And let's just see, analyze here what happens here. So here this is e raised to power j. I can expand this. This is 2 pi n and e raised to power minus j omega naught n. And this is the same as e raised to power minus j omega naught n, right? Which is the same rate of oscillation, except it's in the other direction, right? And you've been able to prove this, right? So my conclusion here is that if omega naught is between 0 and pi, then omega naught and 2 pi minus omega naught have exactly the same rate of oscillation, right? So इसका मतलब आप 0 से अगर बढ़ना शुरू करें तो rate of oscillation बढ़ता जाता है all the way up to pi, right? इसी तरह 2 pi से नीचे आना शुरू करें towards pi, the rate of oscillation increases as well. And where's going to be the maximum? The maximum is going to be in the middle, right? Which is omega naught equals pi, right? So what we conclude here is, which is an important conclusion, is that the maximum frequency or the maximum rate of oscillation is achieved at omega naught equals pi, right? And does that make intuitive sense? You can just take a quick look at what does the signal correspond to when omega naught equals pi. जी दानियाल?
सर आपने जो रेट ऑफ ऑसिलेशन कह रहे हैं, जो हमने एग्जांपल्स किए हैं जिसमें हम सर्कल के ऊपर पॉइंट को मूव करा रहे हैं, इसमें उसमें हम कैसे देख सकते हैं इसको रेट ऑफ ऑसिलेशन को? मतलब कि आप जो पॉइंट मतलब कितने साइकिल्स लेता है?
So rate of oscillation, when I say rate of oscillation, what I mean by that is I can compute the number of samples it takes to complete one revolution. Okay? And the rate of oscillation would be the inverse of that. Right? Which would be the number of cycles per sample.
सर पाई वाले केस में से हम सिर्फ 2 सैंपल लेते हैं और उसमें
एक्सीलेंट, राइट? तो पाई वाले केस में क्या होगा फिर? 2 सैंपल आ रहे हैं, एक 0 पे आ रहा है, फिर पाई पे आ रहा है, फिर 0 पे आ रहा है, फिर पाई पे आ रहा है, राइट? I mean, you're always oscillating between 0 and pi, the angles. Right? तो फिर बनेगा क्या? अगर मैं this is e raised by j pi n, right? And this is e raised by j pi raised to power n. What is this equal to? This is equal to minus 1 raised to power n. Right? Minus 1 raised to power n. And with minus 1 raised to power n, if I just plot this signal, this is a real signal, right? Which would make sense because it's on the positive axis and the negative axis. 180 degrees per sort of shift here continuous, right? And plus pi and minus pi, by the way, are exactly the same, right? Plus 180 degrees and minus 180 degrees. So what does this signal look like? This signal is it's just an oscillating signal. पहले ये है, फिर ये है, फिर ये है, फिर ये है. And if you really think about this, I mean, this is the maximum rate of oscillation that you could get from any signal, right? Because maximum rate of oscillation would correspond to the smallest period, right? What is the period for this? The period is 2. It's 2 samples. And you cannot have a smaller period than 2 samples in discrete time. Think about that statement.
सर आप ये वाला ग्राफ किसी और फ्रीक्वेंसी के लिए बना सकते हैं, मतलब π/2 वगैरह के लिए?
Sorry, फिर से कहें? π/2 के लिए the problem is with π/2 things are complex. Right? The signal is complex. So you have to have a real part and an imaginary part. Right? If you have a real and imaginary part, so I drew that for π/2. Here's where this pink was. Daniel, 1 minute. This pink curve here. right? Which is
yes,
plus 1, 0, minus 1, 0, and then plus 1, and it's a period of 4. ठीक है?
जी सर मतलब इसमें दो मतलब एक फेस का ग्राफ भी बनेगा इसमें.
Yes. अगर आप जो है या तो मैग्नीट्यूड हमेशा 1 रहता है, राइट? फेस का ग्राफ बन सकता है, या फिर यू कैन डू दैट इन रेक्टेंगुलर कोऑर्डिनेट्स. डू द real part separately and the imagined part separately. Okay, so the point I was making here was okay, the rate of oscillation is 2 samples, and that's the so period is 2 samples, and that's the minimum period that you can get for a periodic signal, right? 2 से नीचे नहीं हो सकता, and you would claim that 2 से नीचे 1 तो हो सकता है, but अगर 1 है किसी sample का, किसी signal का period, so what does that signal correspond to? Think about that. That's actually a DC signal. It's a constant signal, and that has a frequency of 0. Right? Achha, so we're running short of time. Let me quickly mention the third point, which is periodicity. Right? I mean, if x of n equals e raised by j omega naught n, can you determine the fundamental period? Right? So if you recall x of t being equal to e raised by j omega naught t, so the fundamental period t was actually equal to 2 pi by omega naught. Can you do the same here? I mean, is the fundamental period here is that equal to 2 pi by omega naught? I mean, is that valid, or is that a valid statement or not a valid statement? Right? I mean, these are the kind of concepts that you need to test yourself, right? To test your understanding. Can this be a period? I mean, can you apply that directly here? So what do you think? Why not, Manur?
Sir, I feel like integer values भी शायद.
Yeah, so excellent, right? So 2 pi by omega naught. I mean, who is to guarantee that 2 pi by omega naught is going to turn out to be an integer? It may or may not be an integer.
Yes,
right?
sir.
And you have to have the fundamental period equal to an integer, right? So therefore, you cannot just blindly apply this formula, if you will, but something that you memorize, right? So you have to go back and see, yeah, what's actually going on. What does periodicity really mean? And periodicity really means what? Periodicity mean, okay, does there exist an integer capital N such that x of n plus capital N, which is equal to e raised by j omega naught n plus capital N, which is equal to e raised by j omega naught small n times e raised by j omega naught capital N. So when is this? This is equal to x of n for all n when e raised by j omega naught capital N is equal to 1. Right? When is e raised by j omega naught n capital N equals 1? Right? This is satisfied when omega naught times capital N turns out to be some integer multiple of 2 pi. Right? Because if it turns out to be an integer multiple of 2 pi, that's when e raised by j omega naught n capital N equals 1. Right? And let's try to do some examples here. Right? So a couple of examples. And then we can end. So x of n equals, let's see if I have. Right, so this is e raised by the same thing that we saw there, right? So 3 pi by 2n. And 3 pi by 2, we found out that the period was equal to 4, right? So it's 3 pi by 2 times small n. And this is periodic. In order to find the period, so to find the fundamental period, the period we need to determine an integer, capital N and small m, such that omega naught times capital N turns out to be some integer multiple of 2 pi, right? And that's how I visualize this, right? So what is 2 omega naught? Omega naught is 3 pi by 2 times N, right? So the question here is, okay, what should N be? What should capital N be such that when you multiply that capital N with 3 pi by 2, you get something which is an integer multiple of 2 pi? What's the answer? The smallest value of capital N which satisfies that property. What is the smallest value of capital N such that when you multiply that value of capital N with 3 pi by 2, you get something which is an integer multiple of 2 pi? And Daniel says it's 4 by 3, right? Excellent, right? So, but Daniel, is 4 by 3 an integer? Right? So you're going back and applying the continuous time principles here, right? That's the problem. I mean, that's the entire, I mean, that's how this is different than the continuous time case. Capital N has to be an integer, right? What is that integer? When you multiply 3 pi by 2 by that integer, you get something which is an integer multiple of 2 pi, and the answer is 4. And as we've seen here, is equal to 6 pi when n equals 4. And this is your fundamental period. Okay? Is no longer 4 by 3, right? Is no longer 4 by 3, but it's actually 4. Now, what's actually going on? Right? If I go back to the cosine, I just visualize the discrete time or the real part, right? So this so 3 pi by 2 was different. So I don't have the time to do that. Do I have the time to do that? Okay, so I'll maybe spend that time in the at the end. I just want to mention another example, which is x of n equals e raised to power j to n. Right? So to find the period, you need to find an integer capital N such that when you multiply omega naught with that integer capital N, you get a multiple of 2 pi, right? So this is equal to 2 times n, right? So find an integer capital N such that 2 times n is equal to an integer multiple of 2 pi. इसका क्या आंसर है? What's the answer to this? Haji Masna.
सर ये एग्जिस्ट ही नहीं करना चाहिए because n should be an integer और pi आएगा ही नहीं उसके साथ कभी भी, I think.
Excellent. So that's exactly true, right? So this can never be, there can never exist an integer capital N such that when you multiply, you can never have two integers multiply together and get something which is an integer multiple of pi. Why? Because pi is irrational. Pi can never be represented as a ratio of two integers, right? So with our conclusion is such an n does not exist. And if such an n does not exist, that means x of n is not periodic, right? And the important conclusion is a discrete time complex exponential may not always be periodic. So that's the final factor, how it's different than a continuous time case. Right? So I will stop here with perhaps an announcement. KG, let's leave that announcement, right? So any questions that you may have. By the way, जो ऊपर वाली सारी थी ना कि वो wraparound effect because of frequencies. If you really understand what's going on, you can extend those ideas to actually derive or at least intuitively understand the thing that you were so amazed by in the last class, which was, okay, sampling, say, you can still recover. Even if you're sampled, you will still be able to recover the original continuous time signal as long as certain conditions are satisfied, right? And this is that condition. I mean, this periodicity in 2 pi is something related to that condition. I mean, think about that. Okay, so I don't have the time to go into those details in the course at this moment. Any question that you may have? So I'll stop you.
So ये जो end पे आपने samples करवाई हैं, इसमें omega naught n is equal to 2 and 2n is actually pi, वो m है, क्योंकि हमारा original our equation was what we need to prove was omega naught n is equal to 2 pi m, right?
Yeah. So you need to find a capital N such that when you multiply the capital N with omega naught, you get something which is an integer multiple of 2 pi. Either 2 pi or 4 pi or 6 pi, whatever.
इससे पिछली example पे जाएंगे आप?
Yeah.
Here we had 3 pi by 2 into n, and we had to prove that it is an integer multiple of 2 pi.
Yeah. So when n equals 4, right? So when you plug in n equals 4 and you multiply it by 3 pi by 2, you get 6 pi, which is an integer multiple of 2 pi, right?
Why can't it be 2?
Because if n equals 2, to pair up, when you multiply 2 with 3 pi by 2, you get 3 pi. But 3 pi is not an integer multiple of 2 pi, right?
Okay, ठीक है.
Well, that's a 1.5 times 2 pi. I mean, that's not what was required.
ठीक है.
I mean, you also think about Talha and all the others. Okay, what does this mean? इसके बारे में सोचिएगा जरा. Okay.
Sir.
जी हमजा.
Sir, ये second example जरा फिर से समझा दें.
या कि ये किसान नहीं है?
Hmm.
Okay. Right. So देखें.